We are discussing our third chapter, Calculus of Vector Fields. Today, we are going to start our sixth module. In this module, we shall mainly discuss the mean value theorem for vector fields. But we shall start with another result which deals with Jacobian of a vector field, which is composition of a scalar field and a vector field. Before entering into mean value theorem, we discuss a result on differentiability of product of a scalar field and a vector field. Similar results were discussed in the fourth module of this chapter, but we prefer to discuss it after discussing Jacobians. The result: let A be a subset of Rn, f from A to R be a scalar field and G from A to Rm be a vector field. We further assume that both f and g are differentiable at a point A, which is an interior point of the set A. We define a vector field H equal to Fg from A to Rm as follows. For every x in A, Hx equals Fx Gx. Now, Fx is a scalar, that is a real number, and Gx is a vector in Rm. So, Fx Gx is a scalar multiple of a vector in Rm by a scalar. So, H is well defined. We claim that H is also differentiable at the point A. Moreover, for every V in Rn, Fg dash A operating on V equal to F dash A V Ga plus F A G dash A V. One thing to note here, whenever we discussed similar results in our earlier modules, we express them as Fg dash A, but never took V with it. We give the proof. Since f and g are differentiable at the point A, for suitable y we can express the increment if f and g as follows: f of a plus y minus f a equal to f dash a y plus norm y e f a y, and g of a plus y minus g a equal to g dash a y plus norm y e g a y. Here f dash a from Rn to R and g dash a from Rn to Rm are linear transformations. Also, as y tends to theta, we have e f a y tends to 0 and e g a y tends to the 0 vector in Rm. Now, we consider the increment of the vector field H. We have H a plus y minus H a, that is f g a plus y minus f g a. We have written down their values here. So, we have finally 8 terms. Those are f dash a y g a plus f a g dash a y plus f a norm y e g a y plus f dash a y g dash a y plus f dash a y norm y e g a y plus norm y e f a y g a plus norm y e f a y g dash a y plus norm y e f a y norm y e g a y. We write down them after separating into two parts. We write it as follows, that is f g a plus y minus f g a equal to t y plus norm y times e 1 a y plus e 2 a y. Here, y is mapped to t y, which is nothing but f dash a y g a plus f a g dash a y. F dash a is a map from Rn to R. So, f dash a y is a real number, we multiply it with g a. So, we have a m vector. Now, g dash a y is a vector in Rm. We multiply with the scalar f a. So, it is also a vector in Rm. Thus, it is well defined. Clearly, T is a linear transformation from Rn to Rm. Let us denote this map by f g dash a. Now, e 1 a y equal to 1 by norm y f dash a y g dash a y, and e 2 a y we define by f a e g a y plus f dash a y e g a y plus e f a y g a plus EF AY G dash AY plus norm Y EF AY EG AY. Clearly, as y tends to the 0 vector, E2AY also tends to 0 vector. As all the 5 terms in the expression for E2AY contains at least one error term. So, we now look at E1. We have norm of E1 AY, it must be non-negative. It equals with 1 by norm y times norm of f dash AY G dash AY. So, this is less or equal to 1 by norm y, norm grad f A norm y, norm of summation L equal to 1 to m grad G L A norm y. So, it equals with norm of grad f A, norm of summation L equal to 1 to m grad G L A norm y. Clearly, as y tends to the 0 vector, this tends to 0. As a result, y tends to theta implies EAY, which is E1 AY plus E2 AY also tends to theta. Consequently, the vector field H equal to Fg is differentiable at the point A. Now, for any y in Rn, we have Fg dash Ay equal to F dash Ay Ga plus Fa G dash Ay. If we want to write this in short, we have to write Fg dash A equal to F dash A Ga plus Fa G dash A, but we have to be careful. Here, F dash A is a linear transformation from Rn to R, Ga is a member of Rm, Fa is a real number and G dash A is a linear transformation from Rn to Rm. Now, let us make the last expression more clear. So, we consider its matrix representation. As f dash A is a linear transformation from Rn to R and G dash A is a linear transformation from Rn to Rm, they are represented by two matrices of sides 1 by n and m by n respectively. Also, Ga is a m vector, so it will be represented by a row vector containing m elements and Fa is simply a real number. In the first term of the right hand side of matrix representation of Fg dash A, as was shown, F dash A is a 1 by n matrix and Ga is a m by 1 matrix. So, in order to make the matrix multiplication meaningful, we write it as follows. Fg dash A, it will be given by a m by n matrix. So, we write it as sum of two matrices. First one, Ga transpose, which is a matrix of size m by 1, multiplied with F dash A, which is a matrix of size 1 by n. We add it with Fa, which is a real number, then matrix of G dash A, which is m by n. So, we have elaborately written it here. Here we have written more elaborately, and we find that the ijth element of the matrix Fg dash A is given by Gia del f del xj A plus Fa del Gi del xj A, and this is nothing but del del xj of Fgi at A, where I runs from 1 to m and j runs from 1 to n. Now, we are entering into the main theme of this module, mean value theorem for differentiable vector fields. We shall state and prove the result, then we shall show how we can derive the mean value theorem for scalar fields from this result. After that, we shall discuss some applications of this mean value theorem. Now, we are going to study mean value theorem for differentiable vector fields. All of us are familiar with Lagrange's mean value theorem for a real valued function of a single real variable. Let us recapitulate it. If a function f is continuous in a closed interval a to a plus h, differentiable in the corresponding open interval a to a plus h, then there exists at least one theta from the open interval 0 1 such that f of a plus h minus f a equal to h f dash a plus theta h. In second chapter module 4, we obtained a similar result regarding vector derivative of scalar fields. Let us recall it. Let F is a map from A to R, where A is a subset of Rn and A is an interior point of the set A. Also let V is a vector in Rn such that for all t belonging to bounded closed interval 0, 1, the vector A plus Tv is in A. We further assume that for all t belonging to closed interval 0, 1, the vector derivatives f dash A plus Tv v exist. Then there exists theta from open interval 0, 1 such that the increment f of A plus v minus Av can be expressed as vector derivative f dash A plus theta v v. But whenever we are dealing with vector fields, an equation like the above relates two vectors in Rm. Whenever we consider f is a map from A to Rm and it does not deal with any value, that is any real number. Let us first check whether we can get some vector equation like this. We cite an example. Let f from R to R2 be given by ft equal to cos t sin t. Then for any u in R, we have f dash t operating on u equal to minus sin t cos t u, that is minus u sin t u cos t. In particular, we restrict ourselves to the bounded closed interval 0 to 2 pi. Then we find f of 2 pi minus f 0 divided by 2 pi minus 0. It is 1 by 2 pi times the vector cos 2 pi sin 2 pi minus cos 0 sin 0, and it is nothing but the vector 0 0. But f dash t is the vector minus sin t cos t, and for any value of t it is never 0 0. So, mean value theorem does not hold, that is, we are not getting any vector equation like the previous one. Let us now state and prove the mean value theorem for differentiable vector fields. Let A be a subset of Rn and it is an open set. Let F be a vector field from A to Rm. We assume that F is differentiable at every point of the set A. Let x, y are members of A such that the line segment joining x and y, which we denote by Lxy, lies also entirely in A. Then for each A in Rm, there exists a z lying on the line segment joining x and y such that inner product A with Fy minus Fx equals with inner product A with f dash z operating on y minus x. Let us give the proof. Since the set A is open, it contains some neighborhood of both the points x and y. As x and y are interior points of the set A and Lxy lies entirely within A, we can extend the line segment with endpoints x and y in both the sides up to some extent such that it still remains inside the set A. In other words, we can find some positive delta such that for all t belonging to minus delta to 1 plus delta, x plus t times y minus x still lies within A. Let A be a fixed vector in Rm. We start with assuming A equal to the 0 vector. Then inner product A Fy minus Fx is nothing but 0. Also inner product A f dash z y minus x also is 0. So, whenever A equal to the 0 vector, there remains nothing to prove. So, we assume A to be a non-zero vector. We define a function g from open interval minus delta to 1 plus delta to Rn by gt equal to x plus t times y minus x. Clearly, g is well defined as x, y minus x are vectors in Rn and t is a real number. Moreover, g is differentiable for every t lying within minus delta to 1 plus delta. Also, the value of the derivative is given by g dash t equal to y minus x. We also define another map phi from Rm to R by phi z equal to inner product Az. Then one can easily check that phi is a linear transformation, and we know that any linear transformation is differentiable at every point of its domain. Moreover, for every z in Rm, phi dash alpha operating on z is nothing but phi z, and by definition it is inner product Az, where A is a fixed M vector. We define another function h from open interval minus delta to 1 plus delta to R by ht equal to inner product A f of x plus t times y minus x, that is phi operating on f of x plus t y minus x, that is phi operating on f g t, that is phi compose f compose g operating on t. By chain rule, h is differentiable at every t belonging to open interval minus delta to 1 plus delta. Also, we find h dash t equal to phi dash f compose g t, f dash g t, g dash t, that is phi dash f of x plus t y minus x, f dash g t u, where u is nothing but y minus x. So, this equals with inner product A f dash x plus t u u, that is inner product A f dash x plus t u u. By mean value theorem of single variable calculus, we can find that H satisfies all the conditions. So, we can assure the existence of a mu lying between 0 and 1 such that we can express h 1 minus h 0 equal to 1 minus 0 times h dash evaluated at mu. That is inner product A f of x plus u minus inner product A f x equals with inner product A vector derivative f dash x plus mu u u. So, this is inner product A f y minus f x equals inner product A f dash z u, where z equal to x plus mu u, and that is lying between the line segment joining x y, as mu is selected from 0 to 1. Clearly, z depends on A. So, this completes the proof. Now, we shall show that the earlier example in which we failed to fit in our earlier version of mean value theorem fits here perfectly. Let A equal to the vector a1 a2, then inner product A f of 2 pi minus f 0 equal to inner product a1 a2 with the 0 vector, so it is 0. On the other hand, inner product A f dash z 2 pi minus 0 equals inner product a1 a2 2 pi times minus sin z cos z, that equals with 2 pi minus a1 sin z plus a2 cos z. Here we can always find such z from the open interval 0 to pi, and we can check it is given by z equal to 0 if a1 is 0, and if a1 is non-zero, it is tan inverse a2 by a1. Now, we prove another result. Let A be an open convex set in Rn, and f from A to Rm is differentiable at each point of A. We claim that f satisfies Lipschitz property on the set A. We start the proof. Let x, y are arbitrarily chosen from the set A, but that must be distinct. If f x equal to f y, then for every positive capital M, we can express norm of f x minus f y less than capital M times norm of x minus y. So, we assume f x differs from f y. As the set A is convex and x y is in A, the line segment joining x and y, which we denote by Lxy, also lies in A. By mean value theorem, corresponding to each A in Rm, there exists z in the line segment joining x and y such that inner product A Fy minus Fx equals inner product A f dash z operating on y minus x, and it is less or equal to norm A, norm of f dash z y minus x. We applied here Cauchy-Schwarz inequality. Now, we put in particular A equal to the vector Fy minus Fx divided by norm of Fy minus Fx. Clearly, A is a unit vector. Putting it in the above expression, we find that inner product Fy minus Fx by norm of Fy minus Fx with Fy minus Fx. So, it is nothing but norm of Fy minus Fx, and it is less or equal to 1 times norm of f dash z y minus x, and that is also less or equal to m times norm of y minus x, where m is summation k equal to 1 to m norm of grad f k evaluated at z, and clearly it is non-negative. Moreover, m is bounded. Hence, the result follows. Corollary: let A be an open path connected set in Rn, F from A to Rm a vector field, and we assume that it is differentiable at each point of the set A with f dash x is the zero transformation from Rn to Rm. We claim that f is the constant map on the set A. We give the proof. We select x and y arbitrarily from the set A with x and y different. Since the set A is open and path connected, the points x and y can be joined by a continuous path and hence by a finite collection of line segments which lie entirely within the set A. Let the n vertices of these line segments be x equal to p1, p2 up to pn, and pn is nothing but y. This will be clear from this line segment. We have drawn a set which is our A, and we have 2 points x and y. As A is not convex, it is not possible that the line segment joining x and y lies entirely within this set, but we can join x and y by finitely many line segments. Now, for all I from 2 to n, the line segment joining pi minus 1 and pi lies entirely within A. Hence, by mean value theorem corresponding to each A in Rm, we can find q1, q2 up to qn minus 1 such that inner product of A with f of pi plus 1 minus f pi equals with inner product A f dash qy pi plus 1 minus pi equals A the 0 operator operating on pi plus 1 minus pi, and it is nothing but inner product A and the 0 vector, where qy lies on the line segment joining pi and pi plus 1. Therefore, we have inner product A with fy minus fx. We recall here y is pn and x is p1. So, we have written it here. So, this equals with inner product of A with fpn minus fpn minus 1 plus fpn minus 1 continues, lastly fp2 minus fp1. Now, using the additivity property of inner product, we express it as inner product f fpn minus fpn minus 1 plus inner product A fpn minus 1 minus fpn minus 2 up to inner product A fp2 minus fp1, and we know it is nothing but 0. As this is true for every A in Rm, we put A equal to fy minus fx, and from the above we get inner product fy minus fx with itself is 0. That is, norm of fy minus fx squared equals 0. So, fy minus fx norm equals 0. So, fy minus fx is the 0 vector, that is fy equal to fx. Now, we recall that xy were arbitrarily chosen elements from the set A, and as a result f is a constant vector field on the set A. We have a remark here. We show that the mean value theorem for a scalar field can be deduced from the mean value theorem for vector fields. Let A be a map from A to Rm, A is a subset of Rm, and A is differentiable at each point of the set A. We further assume that xy are members of A such that the line segment joining x and y lies entirely within A. Now we put m equal to 1, that is, f reduces to a scalar field defined on the set A. By the result corresponding to each A in R, there exists Z in line segment joining x and y such that inner product A fy minus fx equals inner product A f dash j operating on y minus x. That is, A times fy minus fx equals A times f dash z operating on y minus x. Here A, fy minus fx all are from R. So, their inner product is nothing but their product. Thus, we have fy minus fx equals grad f z operating on y minus x for any non-zero A, where we can express z equal to x plus theta times y minus x, where theta lies between 0 and 1. Now, we are going to prove another result. This does not related with the mean value theorem. Before that, we discuss some results from linear algebra. Let E1, E2, Em be the standard ordered basis for Rm. Let T from Rn to Rm be a linear transformation. For every I equal to 1 to m, we define Ti by inner product Tei. That is, for every V in Rn, we define Tiv equal to inner product Tv with Ei. One can easily check that for each I from 1 to m, Ti from Rn to R defines a linear transformation. On the other hand, if for every I from 1 to m, Ti from Rn to R is a linear transformation, then T defined by T1 E1 plus T2 E2 up to Tn En, that is, to be more precise, for every vector V in Rn, Tv is defined by T1V E1 plus T2V E2 up to Tnv En, defines a linear transformation from Rn to Rm. We have the following result. Let A be a subset of Rn, F is a map from A to Rm. We also assume that F1, F2, Fm are the components of F and F is differentiable at an interior point A of the set A. We claim that F1, F2, Fm are also differentiable, and further the converse is also true. That is, if we consider the differentiability of F1, F2 up to Fm at some point A, then it implies the differentiability of F at that point. We start the proof. First, we assume that the vector field F is differentiable at the point A. Then, for all suitable y in Rn, we can express f of a plus y minus fa equals f dash a operated on y plus norm y ef a y, where f dash a from Rn to Rm is a linear transformation and y tends to 0 vector implies ef a y tends to the corresponding 0 vector. Hence, for every I starting from 1 going up to m, we find fi a plus y minus fi a equals with inner product f of a plus y minus fa ei. So, this equals with f dash a y ei inner product plus inner product norm y ef a y with ei. Therefore, f dash a y equal to summation L equal to 1 to m summation j equal to 1 to n del f l del x j at a y j e l. We take inner product of both the sides with ei. So, from the right hand side we have summation j equal to 1 to n del f I del x j evaluated at a y j, because inner product ei e j is nothing but the Kronecker delta I j. So, this equals with inner product grad Fi at A and Y. So, it is Ti y. Here Ti from Rn to R is defined by Ti y equal to inner product grad Fi at A y, and obviously Ti is a linear transformation. Let EFi Ay be defined by inner product of EF Ay with Ei. Now, norm of EFi Ay is obviously non-negative and it equals with the norm of inner product EF Ay and Ei. We apply Cauchy-Schwarz inequality, so this less or equal to norm of EF Ay, norm Ei. Ei being a unit vector, its norm is 1. So, this equals with norm of EF Ay, and we know it tends to 0 as y tends to theta. This shows that for every I from 1 to m, the scalar field Fi is differentiable at the point A. Now, we prove the converse part. We assume that for every I from 1 to m, Fi from A to R is differentiable at the point A. Then for all suitable y in Rn, we can express Fi A plus y minus Fi A equals Fi dash A y plus norm y Efi A y, where Fi dash A are linear transformations from Rn to R, and as y tends to theta, Efi Ay tends to 0 for every y. Now, y tends to theta implies Ef Ay, that is the m vector with components Ef1 Ay, Ef2 Ay up to Efm Ay goes to the vector 0 0 0, that is the 0 vector. Also, T from Rn to Rm, we define it by the following: y is mapped to Ty, which is nothing but f1 dash a y e1 plus f2 dash a y e2 plus up to fm dash a y em. Clearly, this defines a linear transformation. As a result, f is differentiable at A, and this completes the proof. Also, one can easily check that for every I equal to 1 to m, inner product of Ty Ei equals with Fi dash A y and inner product Ef Ay with Ei equals Efi Ay. Hence, we have the following. Let A be an open set in Rn and F is a map from A to Rm. Then F is differentiable at each point of the set A if and only if all the partial derivatives del Fi del xj, I from 1 to m and j from 1 to n exist and are continuous at each point of the set A. Here f1, f2, fm are the component functions of f. All of us are familiar with Cauchy-Riemann conditions, which deals with differentiability of a complex valued function of a complex variable. We show how the differentiability of function of several real variables plays an important role here. By C, we denote the collection of all complex numbers. We can treat C as a linear space over R as well as a linear space over C. Now, a map T from C to C is said to be C linear transformation if and only if it is additive and homogeneous over C. The second condition demands that for every complex number lambda, T of lambda z should be lambda times Tz. Similarly, we can define a R linear map. In that case, instead of the above condition, we should have for every real number C, T of Cz should be C times Tz. Here Z is arbitrary complex number. One can easily check every C linear map is R linear, but the converse is not true. One counter example we have cited here. Consider the map Z maps to Z bar. Now, a R linear map T from C to C is C linear if and only if Ti that equals with T 1 times I equals with 1 times Ti. Also we can say Ti equals to T1i, that is I times T1. So that is a R-linear map T from C to C will be C linear if and only if we have Ti equals with I T1. Now let F be a map from A to C be analytic at a point A, which is an interior point of the set A, and A is also a subset of C. Then for all suitable complex number H, we can express f of A plus H minus f A equals f dash A H plus norm H E f A H, where f dash A from C to C is a C linear transformation like the real case, and as H tends to the origin, E f A H also tends to 0 0. Let f equal to u v. Then the Jacobian of f at the point A is given by del u del x A, del u del y A, del v del x A, del v del y A, where z equal to x y. Now we find f dash A I equal to I f dash A 1 if and only if we have the following, that is the matrix del u del y A, del v del y A should be equal with minus del v del x A and del u del x A. Because the matrix representation of the map A plus IV maps to I times A plus IV, which is minus B plus IA, is given by matrix AB goes to matrix minus BA. Thus we find del u del x A equals with del v del y A, that is ux equal to Vy at the point A, and del v del x A equals minus del u del y A, that is Vx equals with minus uy at the point A. This is nothing but our known Cauchy-Riemann equation. So this completes the proof. In this module, the main theme was the mean value theorem for differentiable vector fields. We discussed it along with some applications. Apart from that, we discussed Cauchy-Riemann equations and other results. We conclude here.